Yeah, so I
introduction. And yeah, so I'll be speaking about the possibility to probe tau g-2 with basically gamma to tau tau reaction in intraperipheral heavy-ion collisions at the LHC. So this is the work done in a few people that are listed here, and maybe I'll go to full screen. Sorry about that. Yeah, and it is based on this paper we published recently. So a few words about the problems, or rather just to give you the background behind this this study. So we are speaking about anomalous electromagnetic moments of tau lepton, and because the tau lifetime is so short, these quantities are so far poorly constrained experimentally. On the other hand, because of the size of the mass of the tau, they can be sensitive to various beyond standard model effects. And just to remind you, the current understanding and the sensitivity we have, the theory value is relatively small comparing to the experimental constraints that are strongest from lab experiments, namely from Delphi, and this is the limit they obtain in a similar process, by the way. And well, this is the leading diagram that contributes to the standard model part, which is called the Schwinger theorem, as you probably know. The second part is the electric dipole moment. This is also highly suppressed in the standard model because it only arises at 3-loop level, and it's around 10 to the minus 34 electron times centimeter, as predicted by the standard model. And here the most stringent constraints come from Bell. However, they are much far away comparing to the standard model. They are the order of 10 to minus 17 electron times centimeter. There are certain Bsm effects that can affect A-tau. Probably the most classical one is the supersymmetry, which predicts the scaling of this of the enhancements with respect to the square of the mass, which gives you this roughly 280 times factor if you compare to the similar quantity from the muon measurements, and also having in mind that there's a tension in the muon sector. Well, it's a perfect case. However, one should keep in mind that the measurement precision for the anomalous magnetic moment of the muon is extremely good, so it will be very unlikely that we will reach even 2,180 times the precision of the AMU measurement. However, there are also some other models that predict slightly different or much stronger behavior with respect to the well, possible non-zero A-tau values. This includes models with leptoquarks, for instance. And another thing is that there are also a big class of Bsm effects that predict CP evaluation in the lepton sector, and they typically also affect the tau EDM, things like extra dimensions, to Higgs dipole model, and again some models with the leptoquarks can easily enhance tau EDM over the standard model value. Quick reminder what has been done at lab. So basically the strongest experimental constraints on tau g-2 come from the similar reaction. EE goes to E goes to tau tau. And basically what was done here is the reinterpretation of the total cross-section for this process. So first, the Delphi measured the total cross-section, and then they put the constraints on the A-tau parameter. So this plot shows you basically how the total cross-section for this reaction changes when you start to have a non-zero A-tau. And here these two bands shows you basically the allowed regions for both A-tau and d-tau at 95% confidence level. And this is just a slide to motivate what we can do at the LHC. So this is a beautiful example of precision tau physics that can be done at the LHC. So this is a recent atlas measurement of the ratio for the branching fraction of W's going to taus over the W's going to muons. So there was this log standing roughly 3 sigma left puzzle, which was recently basically resolved by the much more precise atlas measurements. So what was done here is that the atlas used the top pair events as a clean probe for W's, and the result of this measurement is much more compatible with the standard model and much more precise by a factor of 2 with respect to the previous lab measurement. So the ideas behind this study is, first of all, we'd like to check the sensitivity of this gamma-gamma to tau-tau process in ultraperipheral left-ion collisions at the LHC. At the same time, we'd like to explore differential distribution to gain some sensitivity, and then we'd like to explore the ratios to the standard candle processes, basically to cancel as many systematic uncertainties as possible. And finally, there is also recent work on the same topic that uses effective field theory. So here also the idea was to provide an alternative study to that. So the calculations are pretty simple. We are using the standard approach to fold the elementary cross section with the photon fluxes. We are considering this extra absorptive factor, and we are also using the standard dependence on the elementary cross section with respect to the photon tau vertex function, which has these 3 terms. So this second term can be identified as our A tau parameter when the Q square goes to 0, and then the third term is the t tau times 2 times mass of the tau divided by E, again when the Q square goes to 0. These 2 plots shows you how the elementary cross section for the reaction changes with having 0 A tau. So these are the 2 benchmark scenarios for A tau of plus 0.1 and minus 0.1, and the 2 kinematic variables, the invariant mass of the tau system on the left, and the cosine theta star in the photon center mass frame on the right for a fixed invariant mass. So in both cases, you can clearly see that there is some changes for the overall cross-section value. However, there is also a change on the shape of a certain distribution. So we'd like to constrain or use these two effects to maximize the sensitivity. Concerning the nuclear cross-section, so we have validated those against other available Monte Carlo generators, and in particular, we compared our results for the standard model result with the Starlight prediction. So here, there wasn't a surprise that we got around 20% higher cross-section than the Starlight, and the reason was that in Starlight there are these 2 extra individual impact parameter cuts applied when modeling the initial photon fluxes, which basically changes the cross-section, reduces the cross-section by approximately 20%. So this is a potentially large issue with respect to the theory modeling, and this is one of the reasons why we'd like to build the cross-section ratios to overcome that potential obstacles. A few words about Tau decays. So here we are using a PITIA 8.2 to model Tau decays and also final state radiation corrections. And we spent a bit of time to understand also the effect of spin correlations. So this has to be validated to be quite small in the end, below 1%. And then the good news is that the full calculations of this effect are available since the release of 8.304, and here big thanks to Philip Ilton for implementing basically these extra calculations into the PITIA. On the event selection side, here we are considering basically at least one leptonic Tau decay with minimum PT of 4 GeV, mostly because of triggering the event easily and also trying to reconstruct this easily later on. And few words about the tau reconstruction. So basically, here we are dealing with extremely soft taus, and the typical tau reconstruction algorithms are simply non-applicable, and that we therefore categorize events with respect to the extra charged particle multiplicity. So here we are considering tracks with minimum PT of 200 MeV and eta, absolute eta below 2.5. So you basically have lepton plus 1 charged particle and lepton plus 3 charged particle categories. And basically the selection is really compatible or dedicated for both alphas and CMS detectors. Then the final requirement was to clean out potential background sources. So we decided to apply extra requirement on the PT of the system in the lepton plus 1 charged track category, mainly to suppress the dielectron and diamond background. So these are the two differential distributions that you can obtain at the end of this extra considerations for the Tau decays. The one on the left, this is an example for lepton plus 1 charge track category. So this is the PT of the system. You can clearly see that it peaks towards the non-zero values as opposite to the continuum backgrounds. And the plot on the right, this is the PT of the leading lepton distribution for the sum of all categories, and the different colors denote the different contributions to the final event yield. There are also some interesting correlations when you look at the final state particle kinematics. Basically, what we observe is that all of the energy of all of the variables that are related to the energy of the outgoing leptons or pions are very smeared with respect to the initial tau kinematics. So this is expected because of basically the neutrinos. However, some of the variables that are related with angular variables, for example, the system rapidity, can be in reasonable correlation with the initial tau kinematics. So this is an example of a tau lepton, tau 3 charged track decay, so 3-prong decays and the lepton decays. So here you can see a nice correlation of the rapidity of the di-tau system and the rapidity of the final state particle system. Here, note about possible background. So we did not study this in very details, but we gave a hints what to expect first of all, and how to mitigate or reduce a certain classes of backgrounds, starting from the exclusive diquark production. So those can be reducible with basically extra track veto and extra lepton isolation. So those produce typically many extra particles in the final state. One possible background, which also can be reducible, is the dileptons plus FSR. This again, as I mentioned, can be suppressed with extra system PT cuts, for example. Then the third class comes from the photonuclear process, and for example, the inclusive photonuclear reaction can be reducible by basically requiring 0n topology by using the 0-degree colorimeters. So this is not explicitly considering this work, but this is something to keep in mind when trying to reduce this background. So basically, these are the results of the cross-section calculations after including Tau decays. So in this table, the fiducial cross-section are shown for different values of A tau, the expected number of events for a given assumption on the integrated luminosity and the efficiency of reconstructing the full system. So here we are just doing two assumptions for the integrated luminosity. The first one is that we assume 2 inverse nanobarn, which is roughly the run 2 data set. And then the second assumption is 20 inverse nanobarn, which should correspond to the expected high luminosity LHC assumption. So we can clearly see that we can record at least a few thousand events with existing data and orders of tens of thousands events at the high luminosity LHC. Then we also examine the shape differences of kinematic distributions. So we basically check many distributions, and well, it seems that the PT of the leading lepton has the strongest dependence with respect to the non-zero tau. So this is an example of the modification of the cross section by negative values of the A tau, and then the plot on the on the right. This is the same, but for the positive values of A tau. As I already mentioned, we can also take the ratios to the dielectron or dimuon processes. And before constructing the ratio, we need to fix the fiducial region for that denominator, and this fiducial region closely resembles the fiducial region for the lepton from the Tau decay. And this is the result for the ratio. It's basically typically below 10 to the minus 1. However, non-zero A tau values can modify both the shape and the size of this ratio. And finally, we also checked what happens if we do the ratio with respect to the different assumption of the initial photon fluxes. So here we just did the closure test with starlight. So we basically took the photon flux from starlight, which has this 20% difference with respect to the baseline calculations. And basically what happens after taking the ratio is that this 20% goes down to 5%. However, this extra 5% can be further reduced by full reweighting of the dilepton shape distribution. And after this step, the ratio variable agrees within 1% with the default photon fluxes we are using. And this is the summary of the expected sensitivity at the LHC we can achieve potentially. So we did a simple statistic analysis with extra assumptions on the possible levels of the systematic uncertainties. And as already mentioned, we also assumed two different integrated luminosity scenarios. So basically, this plot on the right shows you that by comparing the best experimental limits from LEP, we can improve them by a factor of 2 with the current run-to data, or by a factor of up to 4 at high luminosity LHC, which can be a nice achievement. We also checked and compared the various numbers with respect to the work that uses effective field theory approach, and here we found out that there's significantly stronger cross-section dependence on A tau, especially at small A tau values when doing things with MATGRAPH and SMEFT SIM packages. This also translates into much better sensitivity on the expected limits when applying also some extra fiducial cuts. So this is still something to understand, and the authors of this work are still trying to do some extra cross checks what is going on. So to summarize, we have done the calculations of the gamma to tau process in UPC at the LHC energies, and we check the dependence on the tau g-2. We have explored kinematic shape variations and also the ratios to various either dielectron or dimuon processes. In our opinion, this should allow us to reach a good experimental precision by canceling many uncertainties. The expected limits on tau g-2 should be by a factor of 2 better with the existing run-2 Atlas or CMS data. and they can be improved by another factor of 2 at the high luminosity LHC. So there is also a nice possibility to do some extra experiments combinations that will obviously further enhance the sensitivity. One word about the expected limit on d-tau. So here we found out that the expected results with the current datasets is competitive with the currently best experimental limits from Bell. So we don't have we don't expect a big improvements here. One possible way that this improvement can come could be the Bell 2 itself. And finally, we have also checked the calculations with respect to the effective field theory calculations, which found out that there is a much stronger cross-section dependence on A-tau. And well, one obvious thing is this can be related with some issue with the EFT coefficients versus A-tau and d-tau conversions. So there are some extra checks that are ongoing, and we do hope that this issue will be understood. Thank you.
Thank you. Those were the talk. Questions? Susan?
Yeah, thanks a lot. This is really interesting news on the Tau g-2. I would like to pick up on the EFT question. So the point is, I think, that you're measuring the tau photon interaction at LHC energies, right? So this means that you don't really extract directly what we call the g-2, which is usually defined as the magnetic, like anomalous magnetic moment at 0 momentum transfer. So in the end, I think it's unavoidable to work in an effective field theory framework. And I mean, it's maybe questionable whether that should be standard model effective field theory, but it's quite likely that at LHC energies, additional interactions will play a role, right? So I think that the framework that this EFT approach is using is more appropriate for the LHC environment, and that probably you could find what you call A-tau, so what you call the form factor, you could probably trace it back to one of the SMEF coefficients that the other framework is using. So it's more a comment than a question. I just wanted to point that out, that to me the SMEF framework seems more appropriate for the LHC measurement.
Yeah, sure, but well, the naive expectation is that these two approaches should be very equivalent. So even in our case, what we are effectively doing is some sort of EFT, but we are using slightly different language, and we don't use all of this EFT machinery, which is typically used by dimension 6 and dimension 8, anomalous coupling studies. So we do expect to have complementarity here. However, well, there is something fishy there.
If I can comment on this, if you go to slide 4, where you show the same diagram at LEP, how did LEP extract the limits? Because it's the same process at the end. I mean, you have quasi-real. My question maybe, is there any difference between the process at the LHC or at LEP?
Well, we checked this, and it seems they are using exactly the same framework as we do. So we did a few checks in a few different, for a few different eta values, and we found relatively good agreement.
Very good. Is this analysis being done in Atlas? And if so, which trigger data sets did you use to do this in LET?
So we definitely started the activity, and well, basically we have like a standard UPC single lepton triggers or dilepton triggers.
So you require a rapidity gap and then a high PT lepton?
Yeah, so for example, at level 1, you select, well, at least one muon, and then you clean out the events at the high level with some extra rapidity gaps and so on.
And I see. And because, I mean, the tau is not like tau decays, in particular the hadronic decays you are aiming at, this will produce tracks and so on and so forth. This does not How did you select the ultra-peripheral condition? If you have more activity than in an usual light by light or dielectron UPC, then?
So we just veto some activity in the forward direction.
Okay.
Which is separated by some amount of rapidity with respect to the tracker.
And you're not affected by peripheral LED interactions, hadronic interactions? I'm asking. Like
yeah, sure. Well, this is why we also propose to have explicit, requirement on 0-degree parameter energy, which will, decrease a bit your signal by maybe 20–30%, but it kills a lot of extra background sources.
Let's see if there are other questions. Roderick.
Yes, thanks for the talk. Just a very quick, okay, sorry, my camera is completely screwed up. Yes. So you said you assumed 20 inverse nanobar for high luminosity at AC, is this correct?
Yes.
So let's say from the machine side, our understanding is that the request is to have 13 inverse nanobar for run 3 and run 4 together, which for the ion operation is essentially high luminosity at AC. Now then, of course, we'll be very happy if we can produce more, but I think we can probably not promise you 20 inverse nanobarns today.
Yes, I know it's not a definite, number, but it's just a benchmark, scenario, which we assume in many studies, including the, yellow reports and so on.
Sure.
But yeah, thanks.
But from the machine side, what we're aiming for is 13, and if we, let's say, could get 20, I think it would be a great result.
Yes.
We'll of course give you as much as we can, but we cannot promise 20 today, I think.
Sure.
Can I add something to that?
Sure, yes, go ahead. And Emilian also.
20, we can look at 20 as a combination between Atlas and CMS, right? So that I think is easily achievable after round 4.
Okay, if you can combine Atlas and CMS, then I agree, yes.
For this, it would be interesting to have the same, ideally the same CATs to make this combination easier.
Yes.
Emilian?
Yeah, I was going to make the same comment that this benchmark is still interesting as at least potential for combination, if we have the same CATs, obviously.
Yes.
And then also here, LHCb can play a role.
Yes, I agree. It can play a role. However, well, it depends how low in PT they can go. I guess much lower than us, Atlas or CMS. Because, well, at higher PT, the rapidity distribution for dileptons gets narrower, and yeah, you basically lose the cross section.
Michael?
Yeah, I just wanted to say that so the numbers that you see here are not so small. So in the end, it could well be that there are some systematic limitations, and maybe even the central barrel of Alice could play a role if in run 3 and run 4.
That would be nice too, yes.
So I know that this is something, an activity that recently started in the UPC group. I mean, not yet very advanced, but at least they have the interest to look into this.
Very good. So the more the merrier. Any other questions to Mateusz? If not, let's thank him again, and let's move now to the monopoles.